Hey there, I'm Amy Kruse. I'm the General Partner and Chief Investment Officer of Satori Neuro, a venture fund that focuses on mental health, brain health and wellness, and the application of neuroscience technologies for human flourishing. I'm excited today to be talking to Dr. Paul Sajda. Hey, Paul.
Hey, Amy, how are you doing?
Good. It's good to see you today.
You too.
Always happy to be in New York and always happy to spend some time with you. You and I have known each other for a very long time.
We have.
Yes, it started back in the day when I was a program manager at DARPA, and you were actually one of the investigators on one of my first programs. So it seems like you've been up to quite a bit since then.
Yeah, no, that got a lot started for me in terms of this neurotech area, and it was exciting times, and it still is exciting times in this field.
Yeah. Well, so some of the stuff that you shared with us today was actually new to me in the fact that you were starting to do this new work with sort of closed loop, TMS, EEG, fMRI, all of these things sort of brought together. How did the confluence of technologies come together for you?
Yeah, so I'm an engineer, right? And so part of this was the fact that I've always believed that combining different modalities together was probably the key in terms of understanding and kind of perturbing the brain and with interventions. And so I had years ago built a system that combined EEG and fMRI, and then started talking to folks who had done fMRI and TMS together. And so we decided to put this whole system together in a way that we could better understand how TMS affected the underlying circuits in the brain related to depression, and how to customize and personalize the delivery of TMS for individuals suffering from depression so as to really better alleviate the symptoms. And that became part of then a closed loop system that we built, first under NIH funding and now under DARPA funding.
Oh, great. So you've continued your DARPA work.
Still back with DARPA, yes.
Yeah, exactly. Well, so, you and I, in some of the times that we had worked together, had worked on kind of human performance applications and things like that. But this is mental health is sort of a newer space for you. Is that true? Or how did you get into, how did you come to focus on these technologies for mental health in particular?
Yeah, that's a great question. So in fact, my research is always kind of focused on elements of trying to understand how humans make decisions, right? And both decisions that are good decisions as well as those that go awry. And so part of the work that I've done in my lab has focused on kind of the basic understanding of that, all at the level of the macroscopic human decision making using multimodal imaging. But then, like with the work we did with DARPA 20 years ago, that was then trying to take some of those fundamental understandings and build systems that could improve human performance. So whether intelligence analysts or athletes. But the key to that, right, was understanding how those circuits could be essentially influenced through closed loop.
Yes.
And now the idea was, well, to take our understanding of biomarkers of good decision making, closed loop interventions, and look at the application in the world of psychiatry. And so that's part of how that Venn diagram got put together to combine those three.
That's great to hear. I'm really curious because, like you said, you keyed on the point of closed loop, right? So some of the data that you presented today was really around using that information about the state of the brain in order to deliver therapy, it seems like in a more efficacious way. Can you tell us a little bit more about how that works?
Yeah, so the idea is, right, the brain is this dynamical system, and therefore when we decide to intervene with the brain, whether it's through neurostimulation or providing even a stimulus to the brain, watching a video, that the time in which that's done and the networks that are active are changing. So in fact, the underlying hypothesis was the fact that there are parts of the brain we're trying to remodel, and those parts of the brain we're trying to remodel are actually connected to one another at certain times. Those times can be influenced by the oscillations the brain is bathed in. And by tracking these oscillations, we can get a better idea of the time in which we need to perturb the brain or provide neurostimulation so as to promote the activation of these networks and the remodeling of the networks.
That's pretty cool. So when we think about the remodeling of these brain networks, obviously TMS is a little bit more shallow, right? It's not getting into the depth of the brain. How are you sort of correlating where you want to stimulate with TMS, the deeper structures in the brain? How does that work?
Yeah, so one thing that we needed to do was build a new type of instrument that allowed us to kind of track these oscillations, the timing, right? and then know that, all right, if we apply TMS at a certain time, what is happening deep in the brain? What's happening deep in the brain is best kind of measured by fMRI, right? And so we can't get the temporal resolution from fMRI, we get that from the EEG, but we can see that we're engaging these deep areas, and therefore whether or not the timing we're applying is efficacious for activating those areas.
Okay, so can you tell us a little bit about the magnitude of change that you saw when you actually used the proper timing and kind of closed the loop?
Yeah, so I mean, once again, it was been very exciting. It's still a small population,
so
right? But
caveats
there.
Yeah.
But we saw basically a doubling in response rate, which means that individuals, their clinical symptoms reduced by 50%. And so we saw that the number of those individuals or the percentage went from 40% to almost 90%.
Wow.
And so, we think that this is now a new way in which to deliver TMS temporally. We're also looking at ways to optimize the spatial positioning because the brain also it's basically this complex system that is operating in space and time.
Right.
And that's another element that we're looking. And we think that if we can optimize those two, we can really make TMS very efficacious.
Yeah. You had said something about biomarkers in the talk, and I was kind of curious about, is this something where you can actually track who's going to respond or how much they'll get better?
Yeah, so that's actually one of the really key insights that we had, which was the fact that you create these systems, and if somebody gets better or not, do you really understand what's going on? And so we looked at two biomarkers that we expected to, in fact, change with this particular therapy. One was the excitability in the brain, right?
Okay.
So one hypothesis in terms of having depression or anxiety is that parts of the brain are hyperexcited. So part of what you're trying to do with neurostimulation is reduce the excitability.
Right.
The other is you're trying to make the brain change. So you're trying to induce plasticity, which is often seen by a change in what's called entrainment, essentially how oscillations in the brain interact with one another.
Yeah.
And what was nice is we saw that with this synchronous delivery, we could track not just from endpoint to endpoint, but over each session, whether, as these biomarkers change, whether individuals were going to move into the zone of being responders or not. And so what that allows us to do is potentially retune parameters on the fly while they're getting the treatment to kind of push them into the responder zone.
Okay. And then I remembered from the data that you presented, you had kind of used the, I'll call it traditional TMS treatment, right, which was sort of over a few weeks.
Right.
But now there are some, accelerated TMS treatments. Do you think that, are you going to test that out as well?
Yeah, exactly. Great question. In fact, we have a new project under DARPA to actually take this approach and use the accelerated, it's called SAINT protocol that will allow us to do this over a period of a week instead of 6 weeks.
Oh, that's fantastic. Because I've known you for a long time, and I know some of the things that you focus on, and you are an engineer, I'm really interested in your thoughts around the eventual deployability of these technologies. So you've described something, you showed us some pictures, there's a person in an fMRI, they've got this coil, this thing, it looks really complicated. Obviously, if you want to get this technology out to the world, you want to have it into something that people can use in the clinic. What are your thoughts there?
Yeah, so we're still in the process of trying to take this first, instantiation that was held together by duct tape and glue and move it now where we have more commercial pieces that are integrated together.
Yeah.
We still want to, I think, improve this in a way where the logistics of doing these scans are easier. It's less of a burden for the patients.
Right.
Right now, TMS is still applied in a clinical setting, or at least in a doctor's office setting.
Yeah.
There are some companies who you know of, like Motif, Neurotech, right, that are trying to do some of this where you could take a stimulator, implant it, and basically use it at home, right?
Yeah.
And they might be interested in the fact that the timing that stimulator should be on should be mapped to what the endogenous states are. So I think that there are people working from kind of the deployment side, the hardware side, the basic science side, as well as the clinical side.
Yeah.
And there's going to be convergence into hopefully a point where we can really make a difference on mental health.
Right. Do you think that you'll ever get out of having to use the fMRI?
Yes. So I think, or at least at the very minimum, be able to get to the point where maybe one only needs one fMRI session, right? And we've been looking at other modalities that we might add to measure activation in the brain that are deep, things like fNIRS. But in terms of setting those parameters, it might be fine to just do that once, dial it in, and then use it for home use, and really be able to reduce the burden of the individual having to come in.
Right.
And also, the other thing that we're looking at is we're doing a study where we're having individuals get treatment while they're engaging networks that we think are involved.
Okay.
Like, so emotional regulation networks. So they're doing a task where they're seeing pictures that would cause a certain disturbed emotional response, right?
Yeah.
And if you can hit the brain at those times, then I think that's really exciting, because you can potentially remodel, as well as in things like PTSD. If you could imagine hitting the brain when somebody's having an episode, that could actually also really impact the efficacy of these systems.
Yeah. You had talked about, we were actually chatting over lunch, and you had talked about kind of mapping fMRI technology, fNIRS, EEG, kind of doing that sort of reverse engineering of the signals. Could you say a little bit more about that?
Yeah, I mean, I think, one thing that the world of machine learning, or those that like to call it AI, has been given us is that there are new ways to think about transforming one set of signals into another set of signals. And so when we have the ability to acquire different signals of the brain at the same time, we can look about how we translate them from one to another. Just like these language models translate English to Chinese, or we could imagine translating, an EEG signal to an fMRI signal. And in fact, one of the approaches or reasons we're interested in this, and this gets back to your other question about how to make this more portable, more usable, is we've been able to show that you can train these models and then on EEG and fMRI, and then later on just have EEG and then use that to construct what the fMRI would have been. So you don't need it. And so this whole idea of computational neuroimaging and new advanced imaging is very exciting.
Yeah. I think that's the way that biomarkers are moving in the brain, not just for mental health conditions, but sort of understanding the brain writ large.
Yeah,
right?
Exactly.
Here we are, BrainMind, New York City. What does BrainMind mean to you? How are you connected to the community, or how has it benefited you?
Yeah, so this is my first time at a BrainMind event.
Okay.
I actually asked you about this, and you said it was a great event, so that's one of the reasons I decided to come. It's actually been great. I mean, I think that it's an exciting place where clearly people with different backgrounds, different experiences, all interested in understanding the brain, the mind, how the brain, when it's under duress or when there's some kind of underlying disease, how can we actually treat it, as well as like thinking long-term about when AI and brain-computer interfaces, how are they going to augment our lives or change our lives? So I think there's great discussions, and it's a community that I feel like I've been a part of for a long time. So it's great to actually be here.
Maybe tell me a little bit more about how you perceive BrainMind ecosystem.
Yeah, no, it's a really interesting question, and we talked already about DARPA, and we know that tackling the brain, the mind, all of these challenges requires kind of a multidisciplinary, multifaceted approach. And DARPA does things that are really risky, and far out there, but they push the science in a certain way. NIH another way. It looks like BrainMind kind of adds to that in a completely different or complementary way, particularly in terms of the philanthropy behind it, the commercialization aspect. It's always interesting to see when a bunch of VCs get together and you don't have to return 8 times. Maybe you can just return 1 time and make an impact. So I think it's really a great organization, and one that's really going to help push us forward.
Well, thanks, Paul. I really appreciate it.
You too. Thanks, Amy.